All right, guys, so this is electron configurations and orbitals, and maybe into quantum numbers. We'll see kind of how long this takes, but this is going to be a little bit of a review from the packet from the other night, as well as an overview of configurations in general. So, first thing we want to do is address the difference between what we call ground state configurations versus excited state configurations. So think about the difference between those two things, right? Ground state is what we would kind of call normal, right? Or following the rules. Or lowest energy. Happy. Right? Any of those phrases would be appropriate. So in other words, like for example, hydrogen's one electron. It in its ground state is going to be in that first box, that level 1s box. Excited state would be anything not normal, okay? So not following the rules, not the lowest energy, right? So it's anything out of the norm we would consider excited state. So what are the rules? Well, you should have figured out there were 3 different rules on how we do this. And if we kind of sketch out an orbital diagram, at least for the beginning here, and so on and so on. So then they had 3s, 3p, so on. So this is called an orbital diagram. Oops. Very much like the boarding house that you guys were talking about in the packet. It's orbital diagram. So what are the rules? There are 3 rules on how to fill this in. The first is called the Aufbau principle, right? And if you remember, Aufbau is actually a German word, and it literally means from the bottom, okay? And so you're filling these in order of energy level. In other words, the first floor will get filled before anything else. So for example, if we have helium that has 2 electrons, those 2 electrons would be both in that first box. We will fill that bottom level before we move on to the next, and so on and so on. Okay? That's the Aufbau principle. So that's the first one. The second one is called the Pauli exclusion principle. And what that one says is that if 2 electrons have to be in the same area, they're going to spin in opposite directions, okay? And that's because, so think about it, electrons are negatively charged. And if they're negatively charged, then what we're going to see, okay, is that they don't like to be near each other, which is why they tend to spread out. If they have to be next to each other, they're going to create a magnetic field in opposite directions. We call that the spin. They're going to spin in opposite directions. Think about 2 magnets. If you were to put 2 magnets together and you want them to stick, you would orient them like this, right? To get them to stick together. So 2 of them are fine. If you brought in a 3rd magnet, no matter what orientation, you're going to force one of these out, which is why a 3rd cannot fit, okay? And so you're going to end up with only 2 that are there, and they have to spin opposite directions. So the way we note that is we use arrows, and we say 1 goes up, 1 goes down. It is sort of arbitrary which one we write as up and which one we write as down. Like, it would be totally fine if I wrote that it went down and then up, you know, like it doesn't really matter as long as if you write 2 electrons in a box, they have to be opposite spin, okay? I would say general convention is that we draw up first, but you're not wrong to draw it down, okay? Okay, last rule is called Hund's rule, okay? And what Hun says is that if you have multiple different boxes in the same level, that you'll fill them one at a time before you start to double up. In other words, again, electrons want to spread out. If they have the opportunity to spread out, they will. So I think the best example we can do is let's work on nitrogen. So if you look on your periodic table and you find nitrogen, it is element number 7, which means it has 7 electrons. So let's fill in those 7 electrons following these rules. We're going to start at the bottom because Aufbau says so. I'm going to put 1 in here. And then Pauli exclusion principle says if I have to double up, I'm going to point it down. So my next box available is 2S, and I'm going to fill that room first. And then I get over to here, and I've only used 4 electrons. I have 3 more to put in the boxes. But these are all on the same level. These 2Ps are all 3 on the same level in terms of energy. So if I can spread out, I'm going to. And do that. So that would be nitrogen's configuration, following all the rules. We filled starting from the bottom. If we do double up, we have them facing opposite directions. And if we can spread out, we will. Quick note, if we did oxygen, which is the next element, oxygen has 8 electrons. So if I added 1 more electron, I would start here. And I would put it there. And so on and so on. Okay? So that's how we do the orbital diagrams. Now, you can probably imagine that this gets very messy when you start having upwards of 30 or 40 or 50 even electrons. So we do have several shorthands on how we do this. But before we talk about that, we're going to look at this in reference to the periodic table. So if I draw the periodic table, it sort of looks like this. And there's an extra section in the bottom, right? So that's the organization of the periodic table, roughly. What we do is we separate it into 4 sections. This is sort of like just helping us figure out like what area of the periodic table we're talking about, right? So this area, those 2 columns right there, the first 2 columns, we call that S. Okay, that's the S block or the S chunk, whatever you want to call it. This part over here, we call that the P block. All right, so if we're referring to an element in that area, the green part, we call it P. Then we have the middle. Okay, so this whole section in here, we call it D. I'm sorry, that was a little bit of a highlighter there, not a pen, but you get the idea. D. And then this chunk down here, we call F. So it's just a way for us to kind of note where on the periodic table we're talking about. Are we talking about something in the S block, the P block, the D block, or the F block? Okay? And so that's kind of how we organize these things. A couple things to note. Up here, where hydrogen is, then there's also up here. So our row 1 is kind of weird because hydrogen's here, helium is here. What should be is that helium, okay, this guy here, should actually be here in terms of like counting things and counting electrons and things like that. So in terms of following the pattern, it should be over in the S block, okay? The reason why we move it over here to the end is because it actually behaves like everything in this last row. And what you're going to see, what I mean by that, is because helium and hydrogen are so small, right, they only have that 1 energy level, and so they only can fit 2 electrons max, right? And so because they can only fit 2, they're so small that they only are in the S area, okay? But helium is quote-unquote full, right? It's happy. It can't take any more electrons in that ring. That's the one exception. Everything else is quote-unquote happy or full when it has that 8th electron, right? This group right here, the noble gases. So we put helium there from a behavioral perspective, but from an electron configuration perspective, we want to think about helium as being right over here next to hydrogen. Okay? Okay. So, talking about configurations and things like that. So I'm going to pull up a picture here. I'm going to insert a picture so I can draw on it. Done. Okay, make this a little bit bigger. All right, so just like I said, we have S, D, P, and F, okay? So how does this work? Let's talk about carbon right here. I want to draw out the configuration for carbon, but I don't want to spend time on an orbital diagram. So the shorthand is, I think they call it the manager's code in the packet, is to just write it kind of linearly. And so if I want to get to the carbon's 6 electrons, I'm going to actually start here in the beginning. And I'm going to read left to right until I get to carbon, because the periodic table is in order of energy, which is the beauty of this thing. As you can see, note here that helium is purple because it should be over in the S block. So here's what I'm going to do for carbon. So this is carbon. 6 electrons. I'm going to read left to right. I'm going to write down everything I read. So how would I describe this electron in hydrogen? Well, I'm in row 1. I'm in the S section, S, and I'm in position 1, box 1 in that section. So then I'm going to keep reading. Now I'm going to run into helium, still in row 1, still technically in the S, but now I'm the second one. So I'm just going to change that to a 2. Now I'm going to keep reading left to right. Now what do I hit? I hit lithium, which is in row 2, but in the S section. And I'm going to keep going through beryllium, 2. So I now have gone through 2 electrons in here and 2 electrons in here. And I'm going to keep reading. Now I'm still in row 2, but now I'm in the P block. So I'm hitting the P. And how many boxes did I go in? I went 1, 2. So the correct configuration for carbon, I would say, is 1s2, 2s2, 2p2. How can I double check? Count exponents. Equals 6, element number 6, we are good. Okay? So that's how we do it. We just literally read right to left. Okay? And just write down everything that you cross through. Where it gets a little bit messy is in the D and the F block. Because if we label these as row 1, row 2, 3, 4, 5, 6, and 7, okay, what we find is that the D block is actually off by 1. Okay? But we put it here because of the atomic numbers of the elements, right? And so if this is row 4, this is 4s, this is actually 3d, this row here. And this is 4d, 5d, 6d. Okay? So the D block is just off by 1 from a energy level perspective. But we keep it in this order because what we see is this 4s section actually has lower energy than the 3D, and so we have to keep it in that order. Okay? So let's try one here. Let's try manganese. Right here, number 25. Read left to right and write down everything, starting with hydrogen. So, reading across, 1. Oops, let me write it down here so we have room. 1, S, 2. 2, S, 2. 2, P, all the way across, 6 boxes. Come down here. 3, S, 2. 3, P, 6. 4, S, 2. And now I'm into the blue part, the D part. So instead of saying, even though I'm in row 4, I'm actually in, running out of room here, 3D, 1, 2, 3, 4, 5. 3D5. So I would say for manganese, 1s2 all the way across, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. And that's where I stop. Okay? So your D should always be one number below whatever corresponding S is next to. Okay? Okay. It gets even messier with the F block. Because if you notice, the F block should be right in there. Should be right in there. Okay? And so what we see is this is actually 4F and 5F. The F block is also shifted down 1. And we'll practice that a little bit more later this week, but that just gives you a sense of where we're going. Okay. Lastly, you can imagine, as this last one did with manganese, that one only had 25 electrons, and it took us a minute to do. So there is a shortcut that you are allowed to do, and it's called noble gas notation. Okay? The noble gases are the last column. We call it group 8, or group 8A, which is this column. Here, let me delete this here. This column here. Okay? Because those are all quote-unquote full, as in like all the boxes in those rows are full, what you can do is you can actually start with those. So with noble gas notation, here's the rule. You go back until the first noble gas you hit. And start with that. For example, if we were going to redo manganese, this one, okay, using noble gas notation, here's what I would do. I would find manganese. I would read backwards until I hit my first noble gas. So I'm going to go back, which means argon is the first one I'm going to hit. So what I'm going to do is say brackets argon, which means all of argon's configuration, and now I'm going to start counting from argon. Okay? So start counting from argon. It's going to put us over here. So I would say 4s2, and now we're in 3d, 1, 2, 3, 4, 5. Okay? That's the same thing. So here we just cut out this whole part of the configuration and said, well, that's just argon. Because if I asked you to write the configuration for argon, you would get 1s2, 2s2, 2p6, 3s2, 3p6. So this is assuming you know that, and we're starting with argon and so on. So can we still use this as an identifying feature? Right? As in to know that we have the right element. Well, yes, because all I have to do is come over here and say, okay, 5 and 2 is 7, plus whatever atomic number argon is, which in this case is 18. And that gives us 25 total, which gives us element 25, which is manganese. Okay? Okay, let's try one more using noble gas notation. I would like for you to try arsenic. Arsenic is right here, number 33. So pause it, try to do noble gas notation for arsenic, and see how we do. Okay, arsenic, number 33. I'm going to use noble gas notation. So So to figure that out, I'm going to go backwards until I hit my first noble gas. So again, we're going to start with argon. Okay, so I'm going to say for arsenic, we're going to go argon 4s2. I'm going all the way through here. 3d, count all boxes, that's 10. And now here, I'm now in the P section, but I'm back up to 4p because it's the fourth row of P that I have. 4p, 1, 2, 3 to get to arsenic. And that is the configuration of arsenic. Okay? There's a few exceptions that we're going to have to talk about next class, but that gives you a great sense of where we're at. So hopefully that was helpful, and we'll talk more about it this week.